Hello and welcome to another lecture on our thermodynamics series. Today's lecture will be on gas power cycles, specifically the Otto cycle, also known as constant volume combustion cycle or spark ignition cycle, and the diesel cycle, also known as the constant pressure combustion cycle or compression ignition cycle. Enjoy! After today's video, you should expect to have a better understanding on how to use the Cold-Air Standard analysis to model ideal versions of the Otto, diesel, and dual cycles. Cold-Air Standard meaning that we will model the working fluid within the cycle as perfect gas air. More to come on that later. And you will also learn how to plot the PV and TS diagram and evaluate the properties at all the important states within all of these cycles, how to apply an energy balance for each of the processes, and finally to determine the net power output, efficiency, and a new performance parameter called the mean effective pressure. Why is studying gas power cycles important? Well, first, for any kind of power generation, it's important to realize that we are facing growing challenges with respect to power generation, electrical power generation. These are due to reduced supplies of non-renewable energy resources, primarily hydrocarbons, as well as a renewed or increasing concern for the effect of using these fuels for power production, concerns with respect to global climate changes. Of course, there's also the fact that our demand for power is continuously increasing. As a result of that, today we're heavily dependent on a whole series of non-renewable energy sources to produce our electrical power. I wanted to also talk a little bit about the fact that these non-renewable resources are not all the same in terms of their environmental impact. We tend to lump them all together as hydrocarbons, therefore they're bad for the environment. And it's true, of course. Any carbon release into the atmosphere nowadays is of concern because of the increasingly significant effects of climate change. However, different types of fuel produce different effects in terms of level of carbon emissions per unit of energy produced, everything else being equal. And so I wanted to highlight this a little bit with this graph from an article that appeared in the journal Nature a couple of decades ago already that highlighted the evolution of the fuels that we use in our power production economy, and that highlights the importance specifically of natural gas as the better fuel for producing power in the long term, meaning that for a given unit of energy, electrical energy produced, the level of carbon emissions that are associated with that are the lowest of all the hydrocarbons. So keep that in mind as you analyze your options for power generation. So let's review a very basic of power cycles in thermodynamics. As we run a cycle which necessarily for a heat engine must be associated with the transfer of thermal energy from a hot reservoir to a colder one, the net power produced through this process is simply equal, with a first law analysis, to the difference between the heat being absorbed by the system versus the heat being released by the system. And with that analysis from the first law, an important performance parameter becomes readily apparent, and that is the thermal efficiency of the power cycle, which we define as usual as what we want. And in the case of this power cycle, this is the net work out of this system is what we want, over what we're paying for, which in this thermal system is the energy into the system that we're going to have in the first place. Typically, this would be in the form of fuel into the power plant. So eta of the cycle, the thermal efficiency of the cycle, is net work out divided by total heat in. The second law of thermodynamics dictates that it's not going to be possible to do this by being 100% efficient, meaning that it's not possible to simply absorb heat from the hot reservoir and not release any heat to the surroundings. Furthermore, the thermal, from our analysis of the Carnot cycle specifically, we've established that the thermal efficiency of these processes tends to increase as the hot reservoir temperature goes up and or the low reservoir temperature goes down. In other words, the bigger the spread between our two energy reservoir's temperature, the higher the efficiency of recycles. A higher thermodynamic efficiency and performance is also associated with a reduction in irreversibilities and loss. However, it's not simply a matter of always trying to optimize the efficiency of a cycle in practice. There are factors beyond simple thermodynamic performance that must also be considered. Typically, economic concerns are also part of the equation. Since the air inside a reciprocating engine is trapped between the piston and the rest of the cylinder, it can be considered to be a closed system. So let's review the conservation of energy for such systems, closed systems. So the work per unit mass is simply the integral of PdV, or the area below the curve to the v-axis. Similarly, on a TS diagram, the amount of heat energy added within a process of a closed system can be represented as the area underneath the curve on a TS diagram. And if the processes can be modeled as being without irreversibility or reversible processes, then by the first law analysis, the areas underneath both of these curves will be the same.
There are two different types of reciprocating IC engines that are differentiated by their combustion ignition process. First, the SI, or spark ignition process, which is most commonly used with gasoline-fueled engines. Here, a homogeneous mixture of air and fuel enters a combustion chamber, is compressed, and is then ignited by a spark, hence the name spark ignition engine. This type of setup scales well, is relatively lightweight and inexpensive, and it's the most common platform used for small engines and passenger car applications to date. The ideal cycle representation for this type of setup is called the Otto Cold-Air Standard Cycle, or constant volume combustion cycle, and this is the model that we'll use to start off our analysis of these types of engines.
The second type of ignition process is called the compression ignition process. It is most commonly used with diesel-fueled engines. Here, air alone enters the cylinder or combustion chamber. It is then compressed to a pressure and a corresponding temperature that exceeds the auto ignition point of the fuel. At that point, fuel is injected directly into the cylinder. The high temperature causes it to ignite without a spark, hence the name compression ignition engine. That type of setup is better suited for larger engines, and it is much more expensive than spark ignition engines in general. It's also the most common platform used for heavy-duty applications. The ideal cycle representation for that setup is called the diesel cold-air standard cycle, or constant pressure combustion cycle. And this is the model that we'll use to start off our analysis of these types of engines. Note that the fuels that are used for these two types of ignition process are different, with diesel fuel, typically DF number 2, having a much higher flash point but a lower auto ignition point than gasoline. Those are the temperatures at which combustion starts with and without a spark, respectively. First, let's talk about some common terminology within IC engines. Note the labels on the diagram at right, which are common to both SI and CI platforms, except the spark plug, of course, which is found only in SI engines. Some important geometric parameters. Top center, or top dead center, is the highest position that the piston can reach within the cylinder, and bottom center would be the lowest point it can reach within the cylinders. And these correspond to a crank angle of 0 degrees and 180 degrees respectively. So to go from top center to bottom center, the crank rotates 180 degrees. The distance between these 2 points, that which is traveled by the piston over these 180 degrees of crank rotation, is called the piston stroke, L. The volume that is swept by the piston as it does that, as it goes from top center to bottom center, is denoted as the displacement volume of the engine. Another important geometric parameter is the compression ratio, R. R is defined as the ratio of the volumes of the cylinder when the piston is at bottom center over the volume in the cylinder when the piston is at top center. When the piston's at bottom center, the volume will be the displaced volume plus the clearance volume, and at top center, it'll be the clearance volume only. So the ratio of those two things is compression ratio R. We'll see later that that's an important geometric parameter that's directly related to the thermal efficiency of the engine. Another important performance parameter is the mean effective pressure, MEP. This is a theoretical constant pressure that if it were to act on the piston uniformly during the power stroke, when the piston goes from top center to bottom center, it would produce the same net work out as the actual cycle does in the entire cycle. You can show that MEP is equal to that net work that's done in a cycle divided by the displacement volume of the engine. In another video, I go through that derivation for you. Now, this is an important performance parameter because for two engines of equal displacement, V sub D, the one with the higher MEP is the one that produces the greater amount of work. And if the engines run at the same speed, then the engine with the greater MEP is the one that produces the more power. Let's talk a bit more about the processes that take place in a four-stroke SI engine for the moment. As the name indicates, the cycle is made up of four distinct strokes, but what's less clear is that there are 6 processes involved in this. So referring to the schematic shown below here, consider that the piston is starting at top center with the inlet or intake valve open. That's sketch A. Stroke 1, as the piston moves from top center to bottom center with the valve open, a fresh charge, which is fuel-air mixture, is entrained into the cylinder. When the piston reaches bottom center, the intake valve closes, the piston starts to move up, and the charge is compressed because the cylinder is closed. In the ideal process, this happens adiabatically and reversibly. Now here's the process of heat addition at the top of that stroke. A spark ignites the fuel-air mixture, which causes instantaneous, ideally, heat addition into the cylinder. Both the pressure and the temperature are going to rise rapidly at that point. Stroke 3, the piston is going to move from top center to bottom center. Again, both valves are closed. This is called a power or expansion stroke, as the piston is pushed down by the hot gases and produces a net work out. It's the only stroke where power is being transferred to the surroundings. At the bottom of the stroke, there's another process, the heat rejection process. The exhaust valve opens, and you get instantaneous pressure relief to atmospheric level, ideally. Stroke 4, with the exhaust valve still open, piston moves back up to top center and pushes the remaining combustion products out of the cylinder. Once it's at the top, the exhaust valve closes again, the inlet valve opens, and the cycle is ready to start all over again. 4 strokes, 2 revolutions of the crank. Let's look at a video that illustrates nicely the whole process and introduces some more terminology for real-life engines.
A car engine generates power from the expansion of compressed air in a contained cylinder with the help of fuel. That is why it's called as an internal combustion engine. Before getting into the working, let's see the main parts involved in the working of an engine. First, the crankshaft. This is the part which converts the linear motion of the piston to a rotational force. Next, the pistons and the piston rods. The pistons will be pushed down by the expansion of compressed air, and turns the crankshaft. And the valves, which controls the flow of air and fuel into the cylinders. These valves are driven by the intake camshaft, and the exhaust camshaft, and the camshafts are driven by the crank itself, using a timing belt. There will be idler pulleys, and a tensioner pulley, to hold the belt tight in place. This here is the internal structure of a 4-stroke, inline 4-cylinder, DOHC engine, which is commonly found in most hatchback and sedan cars. A 4-stroke engine should pass through 4 different strokes to complete one cycle to produce power. They are intake, compression, power, and exhaust stroke. The crank to camshaft ratio is 2:1, which means it will take 2 crank revolutions to complete 1 camshaft revolution. And the camshafts are designed in a responsive manner, to open or close based on the corresponding strokes of each cylinder. Let's take a look at a single cylinder, and see how a 4-stroke engine works in detail. In order to ignite the air-fuel mixture, a spark plug is used. This will ignite the compressed air-fuel mixture, with the help of an electrical spark. We will take it down by each stroke. The intake stroke. The inlet valve opens and the downward movement of the piston creates a suction. This pulls the air-fuel mixture into the cylinder. Once the air-fuel mixture is in the cylinder, compression stroke begins compressing the mixture. At this time both inlet and outlet valves stays closed. At the end of compression stroke, the air-fuel mixture is ignited by the spark plug. The explosion exerts pressure and pushes the piston down. This is the power stroke which produces power to the crank. At the exhaust stroke, the outlet valves opens and the piston pushes out the burned gas. The cycle starts again from intake stroke, keeping the engine running and produces power. For a carburetor engine, the air and fuel are mixed inside the carburetor assembly, and fed to the cylinders. In the case of a fuel-injected engine, the fuel is injected into the intake manifold, or directly into the cylinders. Since only a power stroke produces power, you may wonder how the engine turns continuously. Well, the answer is in the crank itself. The flywheel and the crank counterweights provides momentum, which keeps the crankshaft from stopping immediately. For a 4-cylinder engine, considering any time instance, one cylinder is always in power stroke, which produces more power and less vibrations comparing to a single-cylinder engine. And that is how a car engine produces power in simple. Thanks for watching, and stay tuned for more presentations from Auto Tech Labs.
I hope that you enjoyed this short video and that gives you more insight on the functioning of the 4-stroke cycle engine, the spark ignition cycle. In addition to balancing the power strokes, as they mentioned at the end of the video, you should also realize that there's some concerns about the balancing of each individual piston as they move back and forth in the engine, and that plays an important role on the geometry of the crankshaft and the position of each piston as they are attached to that crank. But that's a topic for a different day. Continuing on our discussion on real engines, let's take a look at what a PV diagram looks like for a real engine actually running. This particular graph was taken from a cooperative fuel research, a CFR engine, that's located at the Engines Lab at Cal Poly in San Luis Obispo. And this particular graph here shows us the variation of pressure versus volume while the piston, a single piston in a cylinder engine, undergoes a full cycle. So you notice the top part of the graph, which shows us the path of the piston as it goes around in the cycle. First, a compression stroke on the bottom, and then the ignition of the charge, peak pressure as the piston is going back down, and the volume inside the combustion chamber is increasing, all the way down to bottom center where the exhaust valve opens. And in real life, the exhaust valve opens slightly before the piston reaches bottom center to allow it some time to equilibrate with atmosphere. And then the exhaust stroke is the stroke that pushes the gases all the way out of the cylinder. The exhaust valve closed, intake valve opens, and we have the intake stroke that sucks the fresh charge back into the cylinder. It closes, and we're back at the compression stroke after that. Similarly, we can plot this data on a pressure versus crank angle graph, and that gives us an indication of how smooth the pressure transition is as the cycle takes place as a function of the position of the crank angle. Notice on the bottom right, the computer program that plots this data, which is called an indicator program, gives us an instantaneous for each given cycle value for the MEP, which we've talked about before, the mean effective pressure, which in this case is 5 bars. The I in front of MEP means that the mean effective pressure is based on indicated power, meaning the actual power produced by the combustion products inside the combustion chamber. This is to contrast it with BMEP, which is the brake mean effective pressure, which would be based on a calculation of the actual power output of the engine at the flywheel, not inside the combustion chamber. Of course, there's losses as work is being transferred from the combustion chamber to the flywheel. All right, how do we simulate the actual combustion of the gases and power produced in a real internal combustion engines? Well, there's a lot of real life processes that are involved here that are more complicated than we're going to see right now. Specifically, the combustion process within the cylinders is a complex process that's associated with many losses. Like, for example, actual heat transfer between the working fluid and the walls of the cylinder, and other losses, like, for example, the fact that the valves do not open instantaneously, the heat added does not happen instantaneously, etc. So at the end of the day, in order to do a very accurate modeling of an actual engine at specific conditions, computer modeling is typically required. And we have these types of software programs to help us do these types of analyses. Nevertheless, we can get a lot of very valuable information with simplified models. So the first model that we use to do this is the air standard model. So the air standard model is based on a series of simplifying assumptions for the working fluid. First, the working fluid in this type of model is strictly air, so not air and fuel mixture, strictly air, which we model throughout the entire cycle for each step, each process in the cycle, as an ideal gas throughout, with constant properties. We are going to model the actual combustion process instead by a heat transfer process. So when the piston reaches top center, for example, at the end of the compression stroke, we're going to assume that it become into instantaneous contact with a very high temperature reservoir, which transfers energy to the working fluid instantaneously. This will be your model for representing combustion. And similarly, during the exhaust process, we are going to assume that when a piston is back at bottom center, that the working fluid in the cylinder is in contact with a cold reservoir, which would be represented here by the ambient condition, and that the remaining heat energy in the cylinder is instantaneously transferred to that cold reservoir before the cycle starts over again, and that all these processes that are taking place in this model are internally reversible, and that means ideal processes. So specifically in the cold air standard analysis, we're going to lock in the value of specific heats, which are going to be critical in our analysis of the cycle as being constant throughout the process, and we're going to pick their value to be those that you would have at the ambient condition. So state 1 in the analysis that we talked about before. All right. For these types of air standard analyses, we can apply roughly the same assumptions and simplifications that I've detailed for the various cycles that we're going to talk about. So it's going to be very similar for the Otto spark ignition cycle, or diesel compression ignition cycle, or a new one called a dual cycle, which is basically a combination of parts of the Otto cycle and the diesel cycle, meaning that part of the heat addition takes place at constant volume, part of it takes place at constant pressure, a process considered to be more realistic compared to real life cycles like the PV diagram I've showed you. And there are many other types of cycles that we can approach as well with similar tools and similar types of analyses later. These different cycles differ primarily in the way that the heat addition process that is used to model the actual combustion is being represented. So to highlight that, in the case of the Otto cycle, again, the heat addition process is going to be assumed to take place at constant volume, and so therefore instantaneous. In the case of the diesel cycle, it's assumed to take place at constant pressure, so not instantaneous. And in the dual cycle, it's going to be a mixture of both of them. All right, let's talk more about the Otto cycle, the constant volume heat addition cycle. This representation of the four-stroke Otto spark ignition cycle that we just talked about actually takes place using only 2 strokes in a series of 4 different processes. Let's go over each one at a time now. Process number 1 is an isentropic compression of the gases, the working fluid, as the piston goes from bottom center B to top center A. During that time, it is assumed that the air that makes up the working fluid that we're modeling here is compressed isentropically, so in a reversible and adiabatic manner, so there's no heat transfer to the outside either. Next is constant volume heat addition to the air inside the engine, which represents our working fluid again, and that heat source would come from the outside. It would be a contact to a high temperature reservoir that is put into contact with the working fluid while the piston remains at top center, so it therefore has to be an instantaneous process. Next is the power stroke or expansion stroke, which consists of an isentropic expansion from 3 to 4. The piston is now back at bottom center. That's our second stroke. And finally, the last process that we have is constant volume heat rejection out to a cold reservoir, which would be the atmosphere, and where the gases are cooled down back to their state 1 instantaneously. And voila, that represents the Otto Cold-Air Standard Cycle, specifically, which we will be using in further analyses. Now note that the compression ratio for this cycle, as we defined before, is the ratio of the total volume and the pistons at bottom center, which represents the volume at position B, which is volume 1 or volume 4, divided by the volume in the cylinder when the piston's at top center, a volume that we call a clearance volume. That's basically the distance, the volume that separates the top of the pistons from the head of the engine when the piston is at its highest point, which corresponds to the volume at point A, which was represented here as V2 or V3. So the ratio of these two volumes is the compression ratio, a very important geometric parameter in the engine. All right. Let's talk about the energy balance for this particular system. And we can apply our first law of thermodynamics to closed system to look at what happens at each of those 4 strokes as we've just defined them. First, looking at each one of them individually, when the piston goes from the bottom center to top center in stroke 1 to 2, the very first process, since that process is adiabatic and reversible, there is no heat transfer. All that happens is work, and work that must be transferred into the working fluid. Applying the first law to this closed system, we see that the work per unit mass is going to be equal to the difference in thermal energy between the piston at top center and where it was at when it began. This analysis here assumes that all the stored energy is only thermal energy. In other words, the effect of kinetic energy and potential energy can be neglected. Similarly, at 3 and 4 during the expansion stroke, it's again adiabatic and reversible. So the work out of the system now is equal to minus delta U, if you will, which is the internal energy of the working fluid when the piston was at top center minus the internal energy that it has when it's at the end of the stroke. This is the work produced per unit mass by this working fluid. In the 2 other processes that take place, they are not strokes, they happen at the end of the strokes. The heat added process is when the piston is at the top of the stroke, the process between 2 and 3 where heat is being added. First law will show us that the heat in is equal to the difference in internal energies. And during the exhaust process, or the simulated exhaust process, if you will, when the piston's at the bottom of the stroke, the amount of heat being rejected is equal to the change in internal energy between 4 and 1, or minus delta U. The thermal energy, the thermal efficiency of the system is the ratio of the net work done by the cycle to the heat added. So based on the above there, we see that the net work would be the work out minus the work in per unit mass. And the heat in is the heat that's been added between state 2 and 3, or U3 minus U2, as shown here. And in another video, we will actually demonstrate that this thermal efficiency can be reduced in the case of this air standard Otto cycle to a simple relationship that involves only the compression ratio and the ratio of specific heat, so stay tuned for that. Since the air standard Otto cycle is composed of only internally reversible processes, the area on a TS and PV diagram can be interpreted as heat and work, and both of those areas are going to be the same. So starting with the TS diagram for heat, the process between 2 and 3 is when heat is being added, and the process between 4 and 1 is being where heat is being rejected. So the difference between those two is going to be the heat added to the cycle, which must be equal to the net work output of the cycle throughout this process, which is illustrated on the PV diagram. So let's take a look at that. The two processes where work is involved during this cycle is between 1 and 2, and then between 3 and 4. So the process between 1 and 2, the surroundings are doing work on the working fluid. So this is considered to be work into the cycle. And between 3 and 4, the working fluid is doing work on the surrounding. So it's work out of the cycle. And the difference between those two, the area enclosed by the PV diagram, is going to be the net work out equal to the heat in that we saw earlier. So looking now at the effect of compression ratio on all this in a qualitative way, clearly if the compression ratio is higher, then the temperature that you're going to have at the end of the compression stroke, the temperature 2 prime, if you will, versus 2, comparing a higher compression ratio to a lower one, that temperature is going to be higher the higher the compression ratio is. If the temperature is higher, then the area encircled on the TS diagram is also going to be larger, as clearly demonstrated here. And so therefore, if the net heat in is higher on the cycle, that's also going to mean that the net work out is going to be larger, since the area encircled on the TS diagram must be equal to the one encircled on the PV diagram. And therefore, that means that the thermal efficiency increases for the Otto cycle as the compression ratio increases, because the net work out is increased. However, the heat added, which is the heat between 2 prime and 3 prime, is equal to the heat added between 2 and 3. Moving on to the air standard diesel cycle now. This cycle is slightly different from the Otto cycle in that the combustion or heat addition process is ideally modeled as taking place at constant pressure, and so our processes are going to be slightly different than before. Starting with the piston at position 1, like before, our very first step is going to be in an isentropic compression, meaning adiabatic and reversible. Once the piston is at top center, we're going to model the heat addition process as taking place at constant pressure from an external source, from 2 to 3, followed by an expansion from the point at which we stop adding heat to the piston being at bottom center point. And that completes the expansion or power stroke. So the power stroke here is segmented into 2 different parts, 2 to 3 and 3 to 4 in the diesel cycle. Finally, once the piston's at bottom center at 4, the last process that returns the cycle to its original point is a constant volume heat transfer from the air from 4 till 1. And that step is very similar to the Otto cycle. So again, the big distinction between the diesel cycle and the Otto cycle is the 2-step power stroke, process 2-3, and then 3-4. As in the Otto cycle, the diesel cycle compression ratio is defined as the volume, the total volume in the cylinder, so the volume as the piston is at bottom center, 0.1, to the volume when the piston's at top center, 0.2, so V1 over V2. But in addition to that, we have the cutout or cutoff ratio, which is the point at which heat stops being added at constant pressure, 3, compared to the clearance volume in the cylinder, which is the volume at 2. So the cutoff ratio is the ratio of V3 over V2. Process 2-3, the heat addition at constant pressure process, is made up of both heat addition and work because the volume is changing while the process is taking place. So the total work given is going to be made up of two different components. The component between 2 and 3, which is going to be the integral of the pressure over volume as usual, and the heat being added over that same process, 2 to 3, is given by an energy balance between those 2 points. So it's going to be applying the first law between 0.2 and 0.3. Heat in minus the work out is going to have to be equal to the change in internal energy. And so therefore we have a component that involves the work that we've just calculated, and a component that involves the internal energy that's calculated. And notice that we end up with a U plus PV term, both at the beginning and the end of the stroke of the process, which is the property known as enthalpy, as we're familiar with. Now, the thermal efficiency of the cycle is again defined as the net work out of the cycle divided by the total heat into the cycle, and using these quantities that we've just established so far, we can see that the expression for thermal efficiency for the diesel cycle is slightly different than it was for the Otto cycle. Note that just like in the Otto cycle, that thermal efficiency is going to increase as the compression ratio goes up. Similar to the Otto cycle, the areas circled on both the TS and PV diagrams have similar meanings, and you can see that the heat being added to the fluid between 2 and 3 is represented by the area underneath the curve, as we showed before, per unit mass. Similarly, the heat rejected between state 4 and 1 is the area underneath that curve. So the net heat added to the cycle, which is equal to the net work out of this system, is simply the area circled by the TS diagram for the cycle. And a similar process happens for the PV diagram and the work out of the system. So both of these areas can be compared for analysis in the air standard diesel cycle like they were in the Otto cycle. Moving on to our last cycle here, called the dual cycle. This is a hybrid of the two cycles that we've just talked about, which is used to try to reconcile the behavior of both the Otto air cycle and diesel air cycle that we just talked about to correspond more closely to a real life cycle like the one I've shown earlier on the CFR engine. So that particular model is broken down into a series of processes, one more than before, and starting with the piston at bottom center, the very first thing that we're going to have is a compression process between 1 and 2, and again we're going to assume that that process takes place isentropically, so very similar. Next, part of what happened in the Otto cycle will be a heat addition taking place at constant volume between 2 and 3, followed by some more heat addition, like in the diesel cycle this time, between 3 and 4, and continuing along that same stroke, right? Because now we're down on the expansion stroke. We're going to have an isentropic expansion between 4 and 5. At 5, we're going to model the heat rejection as we did in both of the other cycles to take place at constant volume between 5 and 1. And voila, we've completed our dual air standard cycle. Efficiency of that cycle can be shown to be, again, a combination of the properties, internal energy, and enthalpy throughout that cycle. Again, a bit of a hybrid between what we found for the Otto cycle and the diesel cycle. And the properties that we use in the analysis of the air standard dual cycle is very similar to what we used for both the Otto and the diesel cycle. And again, the areas on the TS and PV diagrams for the dual cycle can be interpreted as being the total heat added in the case of the TS diagram, and the total work out in the case of the PV diagram, and both of them are going to be the same for the dual air cycle. Tying this to the 4-stroke real cycle that we've talked about, one of the lessons that we learned from this analysis of ideal cycles is that high compression ratios are good. They correspond to high engine efficiencies. So you might ask, well, why not make engines that are continuously higher and higher in compression ratio? And the answer to that, especially in the case of the spark ignition engine, is that we reach a limit before too long. Remember that in the real working fluid of a real engine is a mixture of fuel and air that gets compressed, and at some point that fuel mixture will auto-ignite, causing knocking, causing trouble in the engine, mechanical damage to it. And as a result of that, the real life compression ratio of an engine of a spark ignition engine is limited in the range of roughly 9 to 12 when they're run on unleaded gasoline, which can be increased slightly if we mix that with different alcohols, which tend to have a higher octane rating, which is the fuel parameter that indicates the fuel resistance to this auto ignition process. In the case of the compression ignition or diesel engine, we don't have nearly as bad of an effect on high compression ratio because we don't have a combustible fuel air mixture inside the combustion chamber during the compression stroke. So that's not what's going to limit the design of the engine. But of course, having these very high compression ratio is going to add more mechanical stress to that engine. So that is also a limiting factor for diesel engines. Nevertheless, these diesel engine will pretty much always operate at much higher compression ratios than spark ignition engines, and that's going to allow them to have some advantages like the ability to burn some less refined fuel, which diesel is, and also have generally higher efficiencies than spark ignition engine because their compression ratio is higher, not because the cycle itself is more efficient. And that's it for this lecture on gas power cycles. Stay tuned for next time where we will be talking about the Brayton cycle. Thank you, take care, and don't forget to hit the like video if you enjoyed this video and to subscribe to this channel. Have a good day.